Hi everyone. Uh, my name is Imran. Uh, so the complete name is very long, so let's just stick with Imran for now. My topic today is hyperparameter optimization. It's one of the components in the machine learning ecosystem that we use to train our models. Before we move forward, I would like to apologize because my English is not very good. So I might stutter a bit, but sorry for that. And before I continue, I want to know how many are familiar with basics of machine learning, so I don't spend. Okay, all right, perfect. That's good. So this is me. I work as a head of AI at NeuralGem, but unfortunately, I am switching roles in between. So I will be working in a new company coming month. So but still, this is my current role. Uh, Also, apart from that, I was a scholar, Pi School scholar for AI scholarship in Rome, and these are the three things that I really like. So these will be my topics. I won't waste much time in the start. I will just go right away to the topics. To me, machine learning is basically function approximation. Uh, Normally, what we have is we have the inputs and we pass them through a function and we receive an output. A very convenient example is what I always give is a function. Let's say you want to convert Celsius degrees to Fahrenheit degrees, the temperature, right? The Celsius degree would be your input, and the formula would be the formula that converts Celsius to Fahrenheit will be your function, right? Uh, and you will receive an output. So the function here is the formula. Now imagine in a different scenario, you want to see uh, whether in a picture is it a cat or a dog, right? Now there is no specific formula for that. There is no function for that defined function. So what we do is we assume a function and we try to approximate it. In this case, we have the inputs and the outputs, right? But we don't have the function. In our previous scenario, we had the function and the input, so we calculated the output. But here, what we're going to do is we're going to approximate the function because we already have the input and the output. So this is basically how machine learning works. Is what I call it. There are many definitions, but what I like to how I like to define it is very simple. It's called function approximation. Uh, so these are the, at least to me, these are the, oh, by the before I start, so in this particular scenario, I'm considering only, let's say, semi-supervised learning or supervised learning, not the unsupervised learning. So in this scenario, I say there are three components to a machine learning algorithm, right? So there's the optimization algorithms, there are the parameters, and then there are the hyperparameters, right? Optimization algorithm is the function that tries to converge, that tries to approximate your function, right? So imagine you have this plane, right, and you start from somewhere and you want to reach either one of the local minimas or one of the local maximas depending on your problem, right? This particular component, the optimization algorithms, they will try to reach your defined destination, either it be the local minima or the local maxima. I'm not saying the word global because that is practically impossible. Then you will find the uh, the main part, one of the main parts is called parameters. These are the values or these are the variables that are optimized or that change during the training process, during the process of machine learning when you train them. So here is a equation of a line, and in this particular equation, the y is the output and the x is the input, while the other two two variables here are the weights and biases, and these are what we call parameters, because during the optimization process these will be optimized. And then what we have is something we're going to discuss today called hyperparameters. These are the variables or values that don't change during the or that don't optimize during the conventional training pipeline, right? If you're training an algorithm, you're optimizing some function. These are the values that you pre-select, and they don't change, right? So in this particular presentation, we're going to discuss how we can define the best set of hyperparameters, because selecting the best set of hyperparameters is not an easy task. They previously experiments people conduct experiments to see which hyperparameters work best for general scenarios, and then we apply those particular hyperparameters to all the scenarios. But we can see how we can get a better set of algorithms or of these hyperparameters, right? Again, the problem with them is they're very difficult to select. I mean, there are some general patterns from which you can select, and general rule of thumb from which you can use to get those variables, but there's no defined or scientific way to get these hyperparameters, right? And here I've listed down all the could be examples of a hyperparameter, right? The first one is learning rate. Learning rate is basically the value that defines how big of a jump you should take when you're optimizing, when you're trying to reach your goal, right? How big of a step should someone take? Now it makes sense that you take bigger steps, but then again, if you take very big steps, you will never be able to reach your desired point, because then you're going to oscillate in between. Let's say a convex function, you're going to oscillate at the top, and you won't be able to reach the desired local minimum. In example is in the case of convex function. Then in neural networks or deep learning, you have this number of layers that you can define is also called is also a hyperparameter, and then the number of neurons for each layer, you can also call it as the a hyperparameter. How much neurons should there be in which each layer, right? And then there's the dropout probability. Dropout is basically a technique where you switch off some of the neurons in a layer, right? The idea was that so it's an example that everyone gives about dropout, is such that if you're driving home from bar to your home and you're drunk, and if you can reach home without doing any damage, then you can probably reach home from the bar to your home when you're sober, right? So if half of your neurons are dead and you can still reach, so it means then you can reach when all of your neurons are active. So this is something we do during the training process that helps optimize even better, right? And yep. So there are three solutions, at least three major solutions that help find the best hyperparameters. Only one of them is an actual solution. The other two are just different methods, right? I will start from the very basic one, and it doesn't even work. The initial one, the random search, is basically you find the random. You just sample from the set of hyperparameters you have, and the given value, and you just randomly sample from them. So this does not work at all, right? So we'll move right away to the next one called grid search. So let's assume you have only two hyperparameters here. One is on the x-axis and the other is on the y-axis. What you will try to do is basically you will add them in the x and y order, or maybe if you have three hyperparameters, then it's a hyperplane. But anyways, let's assume you have two hyperparameters here. You will write them and for each set, you will each set of each hyperparameter, you will get a grid like that, and then you can go through this grid, and for each grid you would have to retrain your algorithm and evaluate and see which one gives you the best result, right? But then again, it's very expensive because then you would have to train for all the boxes here, right? So then the better technique here is called Bayesian optimization, right? So what you do is you compute a posterior distribution of the objective function, right? And here you define an objective function, and you do that, and you find the best set by computing the Bayes theorem, using the Bayes theorem, right? I will go into more detail about this one because this is the one that is mostly used and is also used in the AI platform for Google Cloud, right? And I will also go to the Google Cloud uh, a repository I made, which you can use as a tutorial to to go through all the hyperparameter optimizations in Google Cloud, right? So what it does is basically it tries to minimize this function, right? X here is basically the set of all the hyperparameters, and what you're trying to do is you're trying to minimize this function of x, right? So there's, when I was reading about it, there was a example they gave. It's called, it was a simple equation 1 minus x multiplied by exponential raised to power x, right? Now in that particular function, if you put 1, then you will receive the minimum f, which is 0, right? But most of the times our functions are not that simpler. So what we do, so there's a technique then, it's called Gaussian processes, right? So use Gaussian processes to find the best set of to basically use the previous example that you had. You assume in the beginning, and from that, using the Gaussian process, you select the best hyperparameter. So the equation looks something like this. So you have the probability, what would be the probability of hyperparameter, or what would be the score given the set of hyperparameters, and you do this iteratively, and I've written all the steps that you from. So let's call this function a surrogate function, right? And what you do is you have already built a objective function. Then you start with the hyperparameters that perform best on the surrogate function, right? And then you evaluate on those, and then you step back on the second point, right? Find the hyperparameters that perform best on the surrogate, and this is defined based on your previous results, right? So it's an iterative process. Either you run out of time, or there's a time limit that you've added, or there's the max number of iterations that you've added, right? Uh, and the key here is every time you do that, you store the scores of all the set of hyperparameters, so you know uh, which set of hyperparameters gives which score. There's actually in the start, I've given a link that explains the entire mathematics behind this hyperparameter tuning, and it's also by Google. It's the same thing that AI platform uses in the Google Cloud, right? Uh, Again, okay. And these are the helpful resources that I found that correspond to the hyperparameter optimization. Um, okay, is there any way I can move to GitHub, and I want to show something on GitHub here? No, I don't have to log in. It's a public repository I made.
You can just try to go here and share this tab.
Okay, thank you. So this is a small repository I made earlier, and So here, what you can see is I've done this with the with AI platform, Google Cloud AI platform, right? Now the way you do this is you have to run this on Docker, but I think recently you can run it on an editor that they give you as well. But well, let's start with the Dockerized setup, right? So you export all the variables that you want for your project, and I'm assuming that we're doing this in the GCP Bash or either one of a virtual machine in Google Cloud Platform, right? Uh, then you build the Docker image for this particular project for the project you're working on, and this is how the training file looks like. It's a very basic training file. It's a simple linear regression, and here, okay, so you have to import the Hypertune. It's a package also by Google. You can use that hyperparameter module, and here you can define what are the metrics and on what are the hyperparameters, and the hyperparameters are defined here actually. Let me open the SP tuning config. So you have to add a configuration here. You can add a simple a YAML file as a configuration or a JSON file as a configuration, right? And the goal here is to minimize. The max trial should be 50, and so this is something you can choose for yourself. And there are two hyperparameters I have chosen here. Epoch should not be a hyperparameter, but I've chosen this for simplicity. It is an integer type. It can range from 100 to 10,000, and then there's the another hyperparameter which has the type of double, and it can range from 0.001 to 0.009, right? Uh, and once you've added this configuration file, uh, okay, you can go to your train, Hypertune, import the Hypertune, and you just give the, I can't see the, you just give the uh, so you already have the hyperparameter tuning YAML file, configuration file. What you can and it's you have to add it in a specific naming convention so that Google AI platform can pick it up. And once it picks it up, it uses that YAML file, right? And this report hyperparameter tuning metric is something that you see in the logs when you are when in the AI platform you are in the process of training, right? Uh, okay, so let's go back. You build the Docker image. Uh, you push the Docker image to the container registry, and oh, okay. So you can also use the YAML file as a standalone, and you can just give it while not giving it the YAML file in the Dockerized setup, or you can just give it externally, and then you can use the external YAML file. In this case, I used the external YAML file. Uh, so you export you initialize the input variables, and then you just submit the jobs to AI platform. And this is basically how you run the uh, how you run the hyperparameter optimization jobs in the AI platform. It's pretty simple. So the basic step is you create a Docker container, push it on the container registry, and initialize your variables, and then submit that. You don't have to initialize the variables. Just add, if let's assume here you can just add the region, whichever region you're applying as a string, and just submit a job on the AI platform. But for that, I don't think it works on the free part of the Google Cloud platform. You have to enable it first, and for that you have to add the card. But I think so. There are three stages to it. There's a free tier, there's a basic tier, and then there is a, I think the the bigger tier that runs this on a cluster. Uh, so yes, okay. Going back to the slides again. This is the helpful resource that you can use. Okay. Oh, I think I did the questions before, after I submitted the slides. So there's one question I will just ask you here, and okay, assume you have a x-axis and a y-axis, right? And then you have a green color circle in between. So for a circle, you have the x points and the y points, right? And then there's another circle called the red circle, which is inside the green circle, right? And for that, you also have the x and y points. Now, through a linear function, how would I be able to differentiate or classify between the bigger circle and the inner circle? As, assuming a linear line is just this particular line, right?
Just in case, we have some very nice swag to share for those who like to
Yeah.
participate.
Okay. Yeah. Okay. You're done.
Yeah, we have some good swag.
So if you answer this question, you will get some swags, right? I will repeat the question. You have a graph x y, and there's a circle, a green circle in the graph. Uh, that has two features. Let's say the x points and the y points of that circle, and then there's another circle in between inside the bigger circle, which also has these two features, x and y points. Now I want a linear function, basically a simple line that tries to differentiate between these two circles, right? Yep.
Maybe I try the kernel fix, so I add one more feature which is basically x square plus y square and then use that as the set.
Sorry, can you?
No, I was saying I can apply the kernel fix, so I add one more feature which is basically x square plus y square, like square root of that.
Yeah, perfect. So that is the right answer. Yep, perfect. So what you do is basically you have two features. You generate another feature which is the radius, right? And radius formula is r square equals to x square plus y square. So x square plus y square, right? And that is basically how you compute another feature, and through that another feature you can simply use a linear line to classify between the inner circle and the bigger circle, right? Okay, so another question is, so there is a machine learning algorithm called k nearest neighbor, right? Who have heard of it? Okay, in k nearest neighbor, what is the training time in let's say a big O scenario, right? So let's say a bubble sort, it takes O of n square, right? What would be the training time of k nearest neighbor? Yep. No, no, not the evaluation or inference inference time. The training time. What you answered is for the validation or the inference, right? What would be the training time? Sorry, I'm sorry, I didn't get it.
Don't train.
Yeah, you don't train. It's O of one. Yeah, yeah. So it's O of one. And what would be the inference time? Sorry.
Can you repeat?
What would be the inference time to infer? Yeah, yeah. Sorry. Sorry? Nope. Nope. Yeah, it's a trick question. So the inference time, okay. Yep. Nope.
You should go through all the papers. Showing no behavior.
Yep. So you go through all the records, right? Right. So what does that make it? Of n? Okay. Let's assume the k is equals to 1. Then Sorry?
You have to go through everyone to find the first.
I'm not hearing you right. I think a mic would be good.
The last question.
So,
Yeah.
so you
Give me a
need to go through all neighbors,
Yes.
find the nearest neighbor, right?
You would have to go through all the records to find the nearest neighbor.
Yeah, I would say so. Like, if you haven't checked all of them,
Uh-huh. Let's assume the worst case scenario here because we're computing the off
the
end.
nearest neighbor will be the last one who you check.
Yeah.
So it will be linear time.
Yes. Yes. Yes, you're right. It would be off end then. So, yep. Yeah. Okay. One final question, and there is no swag for it. But if you do able to answer this question, you can win a big prize. And you can also win a Turing prize. It's how do you find the global minima? Oh, no, you can't. Yeah, yeah. Yes. I mean, yeah.
What's the answer?
Sorry?
What did he say?
Not possible.
Impossible.
Yeah. Yep, yep.
Through a quantum computer.
Uh, maybe. Yeah. So I think that's it. I kept it pretty short and simple. Thank you, everyone. And I apologize because I stutter a lot and I'm not able to speak good English, but yeah, thank you.